Good afternoon. This is the presentation of our project, Open Set Semantic Segmentation for Multitemporal Crop Recognition. My name is Jorge Chamorro from PUC Rio. The motivation for agricultural crop production is related to the growth in population, which is estimated to be 9 billion in 2050, which increases agricultural production. It's presented here, and it implies some important ecological impacts, which is why it's important to monitor crop production. The task of crop recognition is to assign a crop type to parcels in an agricultural area, and we can use remote sensing to do this because it is cost effective and it is available worldwide. In the latest years, it has improved in temporal and spatial resolutions. We can see this as a task of semantic segmentation. So we assign a class label to each pixel from my satellite remote sensing image corresponding to crop types. And we use synthetic aperture radar sensors because they are almost not affected by atmospheric conditions. We consider the spatial context, but also we consider the multi-temporal context because it's very important. Each crop type has a particular temporal signature that helps us classify it. In a previous work, we used convolutional recurrent networks for classification of agricultural crop types. In this work, we use as a base model a convolutional recurrent network, which is a combination of a UNet with a recurrent network. As an input, we have a sequence of images, and they are applied to an encoder with successive convolution and downsampling operations. The result is a sequence of coarse feature maps, which are the input to the recurrent network. This network is configured as N-to-1, so we produce only the last result. And then we apply a decoder to this feature map for the final semantic segmentation result. In our previous work, we obtained this type of result. Here we have a ground truth for a particular data set, and here we have the classification result. But the white areas here in the ground truth are areas where we don't have a label in these pixels. Here is the classification for the entire satellite image, and we have something interesting here. As an example, this is a municipality, the municipality of Luis Eduardo Magalhães, and it's not present in our crop type classes. There is no class about buildings or city. Here, the algorithm doesn't know how to classify this region because this class is not in the train set. This is what OpenSet is about. So usually we have a closed set classification where we have all the classes that we use during training. We think these are the only classes that are going to show up at inference. But in reality, we want the network to be able to say what areas the network doesn't know, because there may be new classes at inference time. This is sometimes done with anomaly detection, but here we do it with OpenSet, which is a combination. The network needs to learn how to predict the known classes correctly, and also how to predict the areas that are unknown. As a first method, baseline, we have a pre-trained UNet recurrent network, and then we use the softmax values at the output, which might look like this. So this is the resulting image for softmax. We have one channel for each class, and then we apply a threshold value over the maximum softmax value for each pixel. So for example, this 0.65. So if the maximum value of this pixel here is smaller than this threshold, then it is an unknown location pixel. The next method is OpenPCS, which was previously published. And here we adapted because originally it was thought for image, a single image. But here we use it for a sequence, a multitemporal sequence of images. So this method, we take our pre-trained UNet recurrent network, and we put our samples through this network, and we obtain the resulting representation of each upsampling stage. So we take all these representations and we upsample the smaller representations in the decoder so that they have the same spatial dimensions, and then we stack these representations channel-wise. This method then, what it does is this stacked representation, which is a representation for each pixel corresponding to the input image, we fit a PCA, principal component analysis model, for pixel samples of each class. So we obtain one PCA model for each class. And then we obtain the most important features of the PCA representation. We assume that this low-dimensional representation follows a Gaussian distribution. So we apply a threshold over the log likelihood values for each sample. If the sample is outside of the threshold, we classify it as an unknown. There is a problem with OpenPCS, which it has to do with the distribution that we assume, the Gaussian distribution. So the result of the OpenPCA, we assume that it follows a Gaussian distribution with a mean 0 and a covariance matrix corresponding to a different covariance matrix for each class. Here we can see graphically how the distributions we assume for each class may be different. They depend on the samples of each class. In this work, we propose a normalization process resulting in a new approach called OpenPCS++. Here we apply a whitening transformation, normalizing the distribution of each class into an isotropic Gaussian with mean 0 and covariance matrix equal to identity. To do this, we just multiply the result of the OpenPCA times this value, which is the covariance matrix powered to the -1.5 and -1/2. This results in a uniform distribution for all classes, and then the difference is that here we can apply a single threshold value for all classes, a unique threshold value, because they all have the same normalized distribution. This is the advantage, because in the previous method, we applied a unique value, threshold value, but the distributions were different, so this was not optimal. The study areas correspond to highly dynamic temporally areas, tropical areas in Brazil. They are publicly available datasets. First one is called Campo Verde in Brazil. We use a sequence of 12 Sentinel-1 images in this time period. Here we can see the class distribution for this first dataset. It's very changing over time. And in this work, we take the ground truth and we classify for the date of June. For our experiment, we consider as known classes, the important classes, these three corresponding to the samples, the classes with largest amount of samples. The remaining classes we expect the network to classify them as unknown. A second dataset is also publicly available in Brazil. It's called Luis Eduardo Magalhães in this temporal frame. it consists of 12 Sentinel-1 images with 1 image per month. In this case, we evaluated 2 different dates. So we evaluated in June, where we took these classes as known classes, the remaining as unknown, and also in March, with this as the known classes. As a result, we can see the results in terms of a threshold independent metric, because actually the selection of a threshold value is still an unresolved issue, an open research question. And so we use the receiver operating characteristic graphics, and considering the binary classification of known versus unknown samples. And here we have the results for the 3 experiments we did, 1 in the first dataset and 2 in the second dataset. We can see that the proposed normalized OpenPCS++ method produces higher results in general. Comparing with the OpenPCS, we can see a more smoother curve, which might be because of the normalization that allows for a wider range of threshold values to produce better results. As qualitative results, here we have ground truth. Here, the closed set classification, so we don't do anything to detect the unknown. The closed set makes a lot of errors, as we can see here, this area. And we can see also that OpenPCS and OpenPCS++ were better, for example, here. Also, there is something interesting that in this case, a closed set prediction classified this area as incorrectly different class, and the open set methods fixed this by saying this area is unknown, which is better than making a wrong prediction. And this is a qualitative result of the entire image. As I said before, this is a urban area, and we can see that the network says here, I don't know. And also here, this is a no data area, and the network also says, I don't know, which is very interesting. It's better. As conclusions, the open set approach might help us using the network in an operational environment. The proposed OpenPCS++ with the widening normalization improved performance over both baseline methods. And this work evaluated threshold independent metrics, and the definition of a threshold value is still an open issue. Thanks.